Thank you. So as Alex was mentioning, we spent a good bit of time over the past few weeks to introduce Windows machine learning. What we have found is that there are an incredibly large number of scenarios that developers really want to enable in the platform. So having a technology that they can use and depend on is really something they've come to expect from platforms like Windows. And for us, what we really want to do is, as we make that investment something that really can take advantage of all the things that we do inside of the OS and all the hardware that we run on top of it. But when we look at machine learning, the applications of machine learning are growing every day. But what's really interesting is the hardware has made it practical. A lot of what we want to do here, this example in superscaling, is really advances in machine learning coupled with advances in the hardware. And our goal in Windows machine learning is really to take advantage of that core capability and allow you as a developer to use all of the silicon and all the hardware at your disposal to do the things that you want to do in a game. Take the scenarios from character animation, NPC AIs, lots of things that we've seen the last few days, and we'll continue to see innovations in the next coming years. That's what we really want to do as a platform, is give you the capability to do that. The core of Windows machine learning is really simple. Train your model using any framework you're used to, TensorFlow, Caffe, MXNet, CNTK, whatever that might be. Take that model, export it to a format we call Onyx, which is an open source consortium designed for interoperability. Take that model and drop it into machine learning and use it in your game workflow, in your tools, in whatever you want to use it in. And really, as I mentioned, what we're trying to do is make that core platform technology something you can take advantage of your entire game, your development workflow, everything that you might be doing on top of the Windows OS. So really what Windows ML is about is enabling, a number of really important things all together. At the top layer, what we really look at is how do we make it easy for developers to interact with the system and use all the pieces you're used to in all the technology you have. And then at the bottom levels, really use all the hardware. So if I really look at it, we have three layers of the system. At the top layer, there's an API that exists for WinML. The API really has two pieces to it. One is really designed for high performance control. As you're inside of your game, you're used to getting control over all of the resources and all the memory and all the things that really are important about how your game flows. On top of that, the normal app developer is used to things which are kind of simplified for them. So we really provide two forms of the API to allow people to get access to the platform so that it works in a desktop app, it'll work inside of an app that goes into the Windows Store, it'll work with all the things that you expect inside the OS, on top of the OS, whatever you want to do with that technology. The APIs are really driven on top of a runtime layer, which is an engine that's designed to run these models. Inside the core of the model, something that Yuri will go into a good bit of detail on, is a graph of all of these commands, a lot of math about how to run the neural network. That network basically gets interpreted by that runtime that decides how best to use the hardware that's underneath it, builds a graph of how to run that thing, and then it drives that against the hardware itself. At the bottom layer is really the thing that projects things onto whatever hardware might be there. So there's a device layer that basically can consume a technology we call DirectML, which is an ability to project that graph onto whatever hardware might be underneath it. At its most basic form, it projects that onto anything which is a DX12 capable GPU. So any silicon that exists that can run a DX12 driver, we will basically create compute shaders for and use the compute queue and drive all of the processing onto the GPU. We've also used that same technology, that same flow to do that against neural network processors and lots of other types of things. But the real goal is to drive high performance through that interface. So what we call that technology is DirectML. Really what DirectML is about is to take that data flow graph of operators and project it onto the hardware. The interesting thing about machine learning is that it's very much like the graphics workflow in that it is a very intensive workflow in terms of compute, and it is also very, very parallelizable. So we use those same patterns. One of the reasons we chose to go down this direction is that game engine processing and rendering is very similar in its flow. So DML basically takes the core operator graph and, as I mentioned, basically creates basic operators using DX12, HLSL-based shaders, and drives those onto the platform. What we provide in the core of the technology is a baseline set of shaders that work anywhere. So out of the box, as I mentioned, any DX12 capable device, we will create and optimize shaders for all different kinds of platforms. And it really says that whatever is happening inside the engine, whatever type of operator you're trying to run, we will know how to project that to the underlying operator. What we really try to do in doing this is, because it's DirectX and because it's D3D, we basically try to make sure we have a lot of platform coherence. In the game, as you're running and building textures, we want to be able to drive those textures through the machine learning engine. So providing that really core hardware platform gives us the ability to control and unlock all the performance that is available in the hardware. And what we really want to talk to you about is basically how DirectML will manage those resources and manage the interaction with the underlying platform to really get the best possible performance. So one of the things we built with NVIDIA is a technology we call meta commands in DirectML, which allows us to take portions of that operations and interact with the hardware to determine how best to use that specific model of hardware. So if you're on one GPU, it might be, of one class Pascal, one class is Volta, how we understand how to use that hardware best. We now have an interaction pattern to do that, to not only be able to run on anything, but also run the best on the specific hardware that you're looking at. So with that, I'll give it over to Yuri, and he'll explain to you how we do all that.
Thanks, Stuart. So my name is Yuri Uralsky. I work in NVIDIA GPU architecture team, and most recently I've been involved in basically making sure that we can support, as a platform, we can support Windows ML stack at full performance. So as Stuart explained, DirectML is the layer which essentially offloads computationally expensive operations, machine learning operations, to the GPU, implementing them as direct compute kernels. But we can actually do much better than that. So NVIDIA partnered with Microsoft to define an interface. This is the meta command interface that Stuart mentioned, which would allow hardware vendors basically implement these key machine learning operations directly in the driver, leveraging specifics of whatever hardware platform they're running on. So these features might not be available or easily expressible in direct compute, which is why this meta command abstraction is important. So I'll talk about the design of that interface and illustrate how we can achieve that acceleration. So first, I'd like to draw some parallels between machine learning models and functions or regular programs, right? So as you know, any program can be represented as a graph, where nodes in the graph represent operations, and edges in the graph express dependencies between these operations. So here, for example, I have a fairly simple network, very simple program or function. I also added data storage nodes, which include temporary variables which get discarded when the function finishes. It has input parameters, output parameters, maybe some constants. And the goal of the compiler, right, is to take that high-level description and to map it down to the underlying target machine ISA, right? One thing to note is that there isn't necessarily one-to-one correspondence between these high-level operations in the graph and individual machine instructions, right? So for example, today, a very common optimization is to fuse a multiply operation followed by an add operation to a single fused multiply add operation in hardware. So in very much the same way, we can view machine learning models as computational graphs. So here I just replaced some operations. The operations are slightly fancier. So rather than having sort of standard multiply and adds, we have convolutions, we have activation functions, element-wise operations, and fully connected operations here, which are also acting on data, right? And rather than acting on simple data like scalars and vectors, they act on structured data called tensors. And I'll describe what tensors are in a moment, right? So similarly, I can have a textual description of that program. If you used a deep learning framework like TensorFlow or CNTK, this should all sound familiar. So what are tensors, right? So we think of tensors as multidimensional areas of scalars, right? Which are described with number of dimensions, number of elements per dimension, and the numeric type of each element, right? A simple example of a tensor is an image, which is of course something you're very familiar with. A simple image can be thought of as a tensor having large number of pixels in width and height, and only 3 channels or 3 features in tensor speak, corresponding to red, green, and blue components at each pixel. But tensors are much more general than that. So they can abstract data, right? They can represent high-level concepts like whether there is a face present at a particular location on the screen, or they can describe waveforms or textual information. Right, so tensors are data types which our machine learning operations basically process, right? So in this program-centric view of machine learning, again, we think of machine learning operators as these low-level machine instructions comprising an ISA of some sort. Tensors are basic data types that these instructions process, right? And Windows ML Graph Optimizer can be thought of as a compiler, right, which takes this high-level description of a program and maps it down to this tensor machine ISA, the way I'm calling it, right? So in a sense, what we'd like to define is this virtual machine or tensor machine ISA, all the instructions which are useful, which hopefully capture sort of the essence of machine learning, which can be supported by hardware platforms as well as can be targeted by the WinML Graph Optimizer, right? So individual instructions in this ISA are meta commands, which is a new feature of the D3.12 API. So I'll describe what meta commands are in a moment, right? So again, if we look at our simple network, you can quite easily identify operations which can be mapped to meta commands. For example, the fully connected operation at the end can be mapped to a fully connected meta command. So just like any hardware instruction, it will have 2 inputs and it produces 1 output. Again, the data types are tensors in this case, but it doesn't matter. So likewise, the element-wise operation is yet another meta command, again, taking 2 inputs, producing 1 output. And we might want to combine the convolution operation and the ReLU activation function into a single meta command. Again, as I mentioned, we don't require any one-to-one mapping between high-level operations and low-level instructions, and this type of fusing can be advantageous for performance, right? So obviously, in this case, the temporary between the 2 operations can be optimized away if the operation is fused, right? Which can be beneficial for bandwidth and memory footprint. So in general terms, a DX12 meta command can be defined as a self-contained operation or abstract optimized function. This function is defined in the spec. Its behavior is defined in the spec. Each meta command is associated with a GUID, a unique ID of some sort, which the client of a meta command can refer to. It has a number of inputs. It generates a number of outputs. In the context of machine learning or inferencing, these inputs or outputs are tensors, basically arrays of scalars, but the actual meta command API doesn't dictate any particular application, but we're focusing on inferencing in this talk. In addition to inputs and outputs, a meta command's implementation may require some additional resources. For example, it may require some amount of scratch space for its operation. It may require some amount of what we're calling persistent metadata, which is, for example, it might be a lookup table, which is created by the meta command implementation at init time, right? And then the client is supposed to bind that resource at execute time. So it's worth noting that the meta command itself doesn't allocate any memory, right? So all the allocations are done by the clients. Again, aligning with the spirit of the D3.12 API, everything is fully under control of the upper levels in the stack. DirectML, in this case, acting as a client of the meta command interface. So all the memory allocations are done outside of the meta command. So from the client perspective, right, there is a number of steps involved in using meta commands. This is how meta commands are being used by the DirectML layer. First, the client has to enumerate, basically query the list of supported meta commands. Implementations are not required to support all of them. There can be many of them defined, but only a subset of them implemented. Moreover, each meta command can have multiple signatures, and not all signatures, just like a function, can have multiple signatures depending on which data type each signature is operating on. So not all signatures may be supported by an implementation. So the client would create a list of what's available, and then it will basically create a particular meta command instance, particular meta command it's interested in. So it will return a meta command object instance, which can then be referred to in subsequent operations with the meta command. Then the next step would be to basically query, how much temporary space and how much persistent storage is required for a particular implementation. So that will vary from meta command to meta command and from implementation to implementation. Then, of course, there is an opportunity for the implementation to initialize persistent metadata. There is an init call that needs to be issued, and at that point, the meta command object instance is ready to go, right? So it can be inserted into a command list, just like any other draw or a dispatch call in D3.12, and that command list can be kicked off for execution, either on a synchronous queue or an asynchronous queue. So at that point, it's fully on par with the rest of DX12. So the way meta command parameters are described, they're specified in memory structures, right? So for every meta command instance, the client would specify pointers to the allocated storage, right? So for scratch space, you would specify GPU virtual address of that buffer resource. Similarly, you'll do the same thing for persistent metadata. Each meta command would have different options depending on what it's doing, right? So meta commands can be highly parameterized. And for every input and output, of course, you want to describe what they are. Because they are tensors, you want to describe their types. Of course, you want to describe their allocations as well in GPU memory. Each tensor can be described by a particular element type. As Stuart mentioned, we're supporting FP32 and FP16, reduced precision data types for performance for meta commands. Then basically the number of elements in each dimension, the number of dimensions, and the memory layout. So let me describe the memory layout in a bit more detail, right? So we support two different kinds of memory layouts. One is called NCHW, and this is sort of the standard memory layout, which is typically used in frameworks, and it's standard, it's well understood. And that's the layout you would use if you want to interpret the tensor. For example, if you want to read the output of a meta command, you would specify that format. You need to be able to reason about what's in there. Maybe you want to map it to a texture or display it as an image or something like that. But if you have, for example, two meta commands, one feeding into the other, and you're not really interested in understanding, what kind of tensor is flowing between them, then you would want to specify hardware native format, which is opaque. And again, the reason why we decided to define it that way is to allow implementations to optimize memory I/O performance for tensors. So basically, to make it a bit more concrete, I'm going to describe a few examples of meta commands. Actually, only two of them, but they are the most important ones and the most computationally expensive operations in machine learning, which is why it is important for us to be able to expose them as meta commands. So the first operation I'm going to describe is called a fully connected operation. Again, very, very common in machine learning. You have two tensors. We think of them, in this case, we think of them as simple linear arrays of scalars. There is a tensor x on the left-hand side, and the operation produces a tensor y on the right-hand side. And the dependencies between elements in the output tensor and the elements in the input tensor are such that every element in the output depends on all elements in the input, right? That's why it's called fully connected. So each edge, each connection is labeled with a weight. So that's the Wij there. And each element in the output is essentially a weighted sum of the values of all the elements in the input, with weights being the W values, right? It is these weights that are typically learned during the training process. And at runtime, at inference time, these weights are effectively read-only data in most cases. They don't have to be, but in many cases they are. And typically the output of this weighted sum is is given to a nonlinear function, such as a ReLU activation, or there can be others, right? So now let's look at how we can cast this operation into something that we can easily reason about mathematically, and more concretely, a matrix multiplication. So the reason why it is important is because matrix multiplication is a very well understood problem in computing in general, right? So if we can figure out how to cast this operation into matrix multiply, there are plenty of optimized implementations exist. Matrix multiplication is very regular, and implementations can come up with all sorts of ways to optimize the operation and tune it, leveraging architecture-specific knowledge, cache sizes, scheduling, etc. So this should be fairly obvious. The way you do it, we write out the elements of the input tensor as a column vector. Let's call it X. In this case, it has 12 elements. And we write out all the weights as a 2D array, as a matrix. So in this case, the matrix will have 12 columns and 16 rows if the output tensor has 16 elements, right? So we multiply the two together. By definition of a matrix multiplication, each element in the output is a dot product between the input vector and the corresponding row in the matrix. Simple. So the other most important operation in machine learning is, of course, convolution. You should be familiar with it, right? So this is a standard convolution problem. We have an input tensor X. So here I'm following the standard NCHW description for its dimensions, right? So it has 4 channels, 4 features in the depth dimension, and it's 8 by 8 in width and height. And then I have a filter bank consisting of 3 filters, which also have 4 channels in the feature dimension, and they're 2 by 2 in X and Y, right? So I have 3 of them. Maybe I want to, generate an image at the output, right? So we'll call them red, green, and blue. So the way the convolution operation is defined is that we take each kernel in turn and we apply it to the input tensor, sort of walking across the entire tensor. So in this example, I'm showing a convolution with a stride of 3, meaning that the filter kernels do not overlap, but it doesn't have to be that way. Other configurations are possible. In this case, I basically walk the entire tensor, input tensor 9 times, and at each step, I'm evaluating this weighted sum again between the elements in the footprint of the filter kernel in the input tensor and the filter kernel weights, right? So again, it's a weighted sum that we need to produce. As a result, we are producing 9 values. We can arrange them into yet another tensor. So it will have a shape of 1 by 3 by 3. We do the same for green. We do the same for blue. Then we stack them together. And that's the result of our convolution operation. Right? So the result of convolving this input tensor with these 3 kernels is the output tensor of this particular shape. Right? So again, let's look at how we can lower this convolution operation to a matrix multiply. So we'd like to get all the benefits of matrix multiplication here as well. Right? So first, we'd like to figure out how to write out the filter matrix, how to write out the filter tensor as a matrix. So we take each filter kernel in turn and sort of unroll all of its elements into rows of the matrix. So we do the same for green and blue tensors. As a result, we get a matrix which has 3 rows and 16 columns. That's our filter kernel matrix. And next, we do the same for the actual input tensor, where we take all the elements corresponding to filter footprints according to the strides and other parameters of the convolution operation, and we'll write them out as matrix columns this time, right? So again, in this case, our matrix will contain 16 elements in y dimension, basically 16 rows, and 9 columns, right? So you may think that this is a very inefficient way to represent tensor data, right? Because if you think about it, if filter kernels were to overlap, then we'll be redundantly storing the same input tensor elements multiple times in this matrix. But in reality, in most implementations, this matrix doesn't even get written to memory. So this matrix can be materialized on the fly as the matrix multiplication process sort of proceeds. So this matrix can be sort of created on the fly in the register file of the processor, right? So it doesn't have to have any memory footprint. So again, having defined things this way, if we, put the two matrices next to each other, we do the matrix multiplication, our resulting tensor, each element in the resulting tensor, of course, a dot product between the corresponding rows and columns, and then we can reshape it into the output tensor of 3 by 3 by 3. So in both cases, in the case of fully connected operation and the convolution operation, we sort of reduce them down to a fundamental matrix multiplication. And now we're looking at ways to implement a generic matrix multiplication efficiently, right? So matrices we operate on will typically be fairly large. They will contain maybe thousands of elements. They may be stored in global memory, either in row major or column major format, or they may be sort of dynamically be materialized, as I explained earlier. So sort of a standard and naive high school method of multiplying matrices where you have sort of triple nested loop, walking over the elements of the output matrix one by one, and computing the full dot products between the two input matrices is actually very inefficient, right? So as you're doing this, you can clearly see that every row and every column of the input matrices will be redundantly read multiple times, and if the matrices are large, then it is very likely that the implementation will end up thrashing caches and be very inefficient in terms of its memory access performance. So a much better approach is to basically tile the matrix, right? Subdivide the matrices into a set of tiles. And then rather than computing full dot products at every step, we're computing partial matrix products, and we essentially accumulate them into the destination by walking the corresponding columns and rows of tiles, right? So again, the specific detail of what the tile sizes are and how exactly the algorithm iterates over the matrix space are highly implementation specific, right? So again, they will depend on things like what the cache size of a particular machine is, what the scheduling details are, et cetera, et cetera. So implementing this sort of algorithms in standard direct compute is very difficult if you want to capture all available performance, right? So again, for this type of operations, the meta-command abstraction makes sense. In fact, we can go even further and sort of implement the partial matrix products also in this fashion by tiling them, right? So there is a hierarchy of operations that you can imagine, and by doing things in this hierarchical fashion, you can more closely match the hierarchy of the target processor, which is again something very, very implementation specific. You don't want to implement it in a generic code. So as you see, it turns out that sort of the most fundamental inferencing operations can be reduced down to matrix multiplies, large matrix multiplies. Large matrix multiplies in turn can be expressed as a sequence of small fixed size matrix multiplies, and this is where tensor cores come in, right? So on our recent GPU architecture called Volta, we introduced a new SM design, which, along with many other improvements around programmability and efficiency, introduced Tensor cores. Right? So Tensor cores are specialized data pods in hardware, which are specifically designed and optimized for machine learning operations, machine learning acceleration. Right? So for each SM, we have 8 Tensor cores. These are the green boxes on the right. And collectively, they're capable of performing up to 512 fuse multiply add operations per clock. Right? So it's a huge amount of floating point performance. To put things in perspective, regular FP32 performance is roughly, well, it's exactly 64 FMAs per clock, so there is a factor of 8 potential difference in peak performance, right? So on Titan V, which is our highest end consumer GPU, we're talking 110 teraflops of floating point performance. So what Tensor cores do, it turns out that they're hardwired specifically to perform this fixed size matrix multiply accumulate instructions or operations, right? So given input matrices A and B, the Tensor cores compute their products, and then they add the result to a third operand C, storing it in the output, right? The operation is done as what is called a mixed precision mode, where A and B matrices are represented as FP16 data. The multiplication is done in FP16, but then the accumulation is actually performed at full precision. And as you can imagine, that's actually important for the type of algorithm I explained earlier, where we're sort of repeatedly accumulating results of partial matrix multiplies into the destination. So Tensor cores employ all threads on the warp to provide data for the input matrices, right? So the way it works is that you have 32 threads running. At one point, they synchronize, provide matrix data into the downstream math data paths. Then the operation is carried out, and the result is written back to the register file. The specific details of how the matrices are split across participating threads is, again, very, very hardware specific, implementation dependent, which is why this operation is kind of hard to express in standard direct compute terms as a standard direct compute operation. So we need a higher level abstraction here. And secondly, actually fully taking advantage of this type of machinery requires carefully tuned code, which is only possible, again, if you make assumptions about what hardware you're running on. So in optimized implementations, Tensor core usage can provide substantial performance speedup. So this is measured in our linear algebra package, performing sort of standard matrix multiplies on a fairly large matrices. There is an almost an order of magnitude performance increase relative to our previous design, the Pascal hardware. So now to illustrate the kind of performance gains that can be obtained with medicaments in real application, we actually have a demo that I'd like to show. Okay. Okay. I'll put it here. Right. So what this demo is doing is it's capturing a live video feed. So I have a camera here. And it post-processes the video feed, applying to it a particular art style. So it's not entirely obvious what's going on here, but the picture on the lower left corner is the famous Starry Night picture by Van Gogh. And this basically, this demo is based on a white paper which was published a while ago called A Neural Algorithm for Artistic Style, which made a very important observation that if you have a neural network, let me point it to Stuart to make it more interesting. If you have a convolutional neural network which is trained to recognize objects, as a side effect of the training, it will abstract both the content of the image, of the images that has been trained on, as well as the style. And these are two separate representations. So, and then if we extract the style representation from the network and use it separately, then we can apply this art style to an arbitrary image, which is what is going on here. So it tries to understand what it is about Van Gogh, like in the way he drew his paintings. So we actually have a number of different art styles. So it's not just Van Gogh, but for example, I'm sorry, I don't know the painter's name here. I'm not really good at that. But basically, cycling through them. Yeah, this one I know. This is Kandinsky.
So the same network has been retrained with different painters. So it is the same actual network structure, just applying different weights from those matrices to define how the output will look.
That's right. That's right. So basically, the network was trained on examples of these pieces of art, and now it has learned the specifics of the art style. So this is kind of cool. Let's see. That's me. That's you. What else do we have here? Yeah, so you can play around with this thing. It's kind of fun. We actually have this demo running in the booth, so you can go and check it out. But the main point we're trying to make here is that this network is extremely computationally expensive, it turns out. So currently it's running in real time, basically at the speed of the live video stream. Well, it's dropping a bit, right? But let's assume it's running at 25 frames a second. Post-processing the live video feed in real time using meta commands and Tensor cores. So now it's running in Tensor core mode. So now
the camera is 1080p.
The camera is 1080p, right? So this is a full HD image being processed at full resolution at 25 frames a second, right? So if we switch the meta commands path off, it becomes a lot slower, much more choppy, right? So this is the baseline DirectML path, which uses direct compute, sort of generic code, which implements everything. But because it's generic, it cannot take advantage of all the hardware specifics, cache sizes, etc. It doesn't use Tensor cores. And we have two variants of the meta command path. One I've already shown. This is the Tensor core path. Let's look at it again. Right, so it's running much faster. So this is using FP16 and Tensor cores. And this is using meta commands, meaning acceleration, but not using Tensor cores. It's running slower. It's running at 8 frames a second, but not as slow as the basic generic path. So it sort of demonstrates the value of having an abstraction which can be accelerated by implementations behind the application spec. This is really the essence of the meta command interface. Okay, so yeah, I encourage you to come visit our booth and play with the demo. It's kind of cute. Right, just a few facts, sort of interesting facts about the demo itself. It's actually comprised of 16 convolutional layers, right? So Stuart mentioned the camera feed is 1080p, 1920 by 1080, which are being progressively convolved 16 times in sort of depth dimension. And at the end, you have another full convolutional layer spitting out the post-processed image. So if you count up the total number of operations that we have in the network, it turns out to be 640 billion floating point operations per evaluation, per frame. It's a huge amount of compute work that's going on here. And with the meta commands path, we're able to achieve 80% of peak Tensor core performance in most convolutional layers, which I'll call pretty good, right? So we still have some headroom, but it's close to peak, right? Translating it to teraflops, we're talking 88 teraflops compute density out of 110 available on Titan V, right? Another cool thing about the demo is that we actually started working it quite late in the process. And we were preparing for GDC, all the pieces in the WinML stack were sort of coming together. But it turned out that it was fairly easy for us to take the existing trained model. So this one thing I didn't mention, and I apologize for that this isn't a new demo. This demo was shown at GTC last year. This is something we worked on last year, but the demo at GTC was using our own proprietary CUDA interface. This is a WinML version of the same demo. And it turned out that it's very easy for us to take the trained model from last year and essentially plumb it through the WinML stack. We implemented necessary meta commands, and we had the demo ready. So it was very easy to go through the entire process end to end. And just summarizing performance, these are the numbers that we're talking about. Again, with Tensor cores and meta commands, we're getting real-time performance, which is really, really hard to achieve without meta commands. As you can see, even with FP32 meta commands, not using Tensor cores, we're not quite there yet. And again, the baseline DirectML performance is really not acceptable for this particular application. So this is taking things a bit too extreme, but this is demo just to illustrate what kind of performance gains are possible in principle through this accelerated path. So we're talking about 8x performance difference relative to the baseline. So basically, to summarize, so we've talked about DirectML. DirectML implements core machine learning operations as direct compute kernels. This has the benefit of the breadth of support. Any direct compute implementation can run them. But to really extract the full extent of performance offered to specific hardware platforms, we need this new interface called meta commands, which allow implementations export optimized versions of these operations, right? And we have everything that's needed as a platform, both in hardware and in software, to accelerate support for machine learning. We've been working closely with Microsoft on that. Machine learning is here. It can be used in games today. Please start thinking about what you can do with it. There is lots of interesting things going on. I encourage you to visit our later talks on use cases of machine learning. And Windows ML is available now in Windows 10. So one last thing, just a shameless plug. We have another conference next week. So if you haven't registered, you still have time to get the 20% savings. So thank you.
So if there are any questions, we're happy to answer anything about the talk or what we're doing. If you want to ask, there's a mic right there.
Do you guys plan on open sourcing that demo?
Open sourcing the demo. I think that the models are already available on GitHub. You can go and download them in Onyx format, right? So in that sense, it's been already open sourced. The actual code for the demo itself, as I explained earlier, is very compact, right? Because WinML essentially does everything for us. We don't need to do much. As far as actually open sourcing that code, we haven't discussed that. That's a possibility, I guess.
Yeah, so we've put a large number of samples up in GitHub. We could find out whether this specific demo code will go up there as well. I'll take the action to take a look at that. It's D3D code and WinML, and that's about it. All the rest is underlying code.
Right.
So like the rest of it, I think there's no real reason why we wouldn't. I'll find out.
When you're profiling it's a game, it's hard enough already today just trying to get the frames per second. Adding in this to the GPU load and trying to analyze that. How are you going to do that with the profilers?
So we have added support already to PICs so that you can see the GPU timeline and the ML specific events. So you'll see DirectML calls for each of these operators in the PICs timeline. So basically we are actually really looking at that problem as a very important one to solve to make sure you have very tight control over what happens where.
Okay.
Will meta commands be exposed as an interface to users as well? Right now, it's just on NX that you can
So the original intent of meta commands was a sort of, let's call it, engine to hardware interface to enable us to really sort of go through this interchange with the hardware to get the best performance. Whether that API is public or not, it's currently not public in the current Windows 10 distributions, but it is something we're looking at. As Yuri sort of pointed out, it is a D3D12 API. We don't know whether it will be public or not, but it is definitely something we're considering.
Would be, if you are not exposing it, for instance, writing a custom operations, how would that be implemented then?
So meta commands are different from custom operations in that meta commands are very specific, as Yuri sort of noted. We'll put a GUID on something that says this is a fully connected operation. So no matter what graph we get from anywhere in Onyx, we can map it to that meta command. If you create a custom operator, we'll have an SDK later this year that allows you to wrap all of your shader code in there. If that wants to call a meta command, it would be, what I'm trying to figure out is we'll have to figure out what that looks like. I don't know the answer.
Thank you.
So in your slide, you were showing how the transformation could be mapped to a meta command or like a set of meta commands. And I was wondering,
the first few slides?
Yes. How does so it's going to be the WinML layer which is going to pick what meta command are going to be used, or is it going to be the DirectML layer?
So what we do today in Windows ML Engine is there's, as Yuri sort of described, it's kind of like a graph compiler. Mm-hmm. It will look through the tree and try to understand what meta commands are available and how to map best the tree to those things. So in some cases, it can choose a node by node. In other cases, he showed that we can fuse things together and choose a fused implementation. So the higher level of the WinML runtime itself will basically do that graph compilation.
So do you think there'll be some some combination which may be faster on some platform and some others? How are you going to deal with, because it's going to be a platform.
So that's why we call it a compiler, is that in reality so there is a good element of cost-based optimization to understand that one device, right, may be very different in profile from another device. So what we really try to do is understand, like if you look at the meta command interface, it'll tell us what the scratch space of something is. So we can look and see if the memory requirements are very high from device 1 versus device 2 versus what we have in the system. It mostly comes down to cost-based optimization. How fast is it on what platform? It's a fairly complex problem, right?
Right, but you don't have any int besides like scratch space, for instance. So like do you plan to like add some int or like on the cost of like a meta command or like?
So in the meta command today, there is not a cost interface. We don't ask the meta command what its cost is. What we do is behind the scenes, we measure it. So we understand how to keep track of that data, right? But in the reality is where it evolves from here, to the question was asked earlier, that's something that we're really sort of trying to evolve with this sort of, let's call it machine interface, is understand how to best use that hardware. One of the things that gets hard is that it sounds always, awesome to use the best possible thing, but also what has to be taken into account is dependability, which is that if you're trying to do I need to control what happens on what timeline, you don't want us switching over to something we think is higher performance. So what we're going to try and do in the D3D12 spirit is expose that to you as a developer, let you choose, and then control how that evolution happens.
Right, and one thing I'll note is that it's still fairly early, right? Things will evolve, between now and then, and the overall field of machine learning is rapidly evolving, right? So there will be more changes coming.
Thanks.